Welcome to Chapter 2 of our Natural Language Processing series. In this chapter, we'll explore how deep learning has revolutionized the field of NLP. We'll start with the fundamentals of recurrent neural networks and work our way up to sophisticated architectures like LSTMs and attention mechanisms. These neural network approaches have enabled breakthrough performance in tasks like machine translation, sentiment analysis, and text generation. Let's dive into the world of deep learning for NLP. Why has deep learning become the dominant approach in NLP? Traditional NLP relied heavily on handcrafted features and rules designed by experts. This required significant domain knowledge and was often brittle. Deep learning changed everything by enabling automatic feature learning directly from data. Neural networks can discover patterns and representations that humans might never design. They also enable end-to-end training, where the entire system is optimized together. The results speak for themselves. Deep learning models consistently outperform traditional approaches across virtually all NLP benchmarks. Recurrent neural networks, or RNNs, are designed specifically for sequential data like text. Unlike feed-forward networks, RNNs have connections that loop back, allowing information to persist across time steps. When processing a sentence, the RNN maintains a hidden state that acts as a memory of what it has seen so far. At each time step, it combines the current input with the previous hidden state to produce a new hidden state. This architecture naturally captures dependencies between words in a sequence, making RNNs well-suited for language modeling, text classification, and sequence labeling tasks. However, vanilla RNNs suffer from a critical problem, the vanishing gradient. When training on long sequences, gradients can become exponentially small as they propagate back through time. This means the network struggles to learn long-range dependencies. If a relevant word appeared 50 tokens ago, its signal may completely vanish before reaching the current position. This is particularly problematic for language, where meaning often depends on context from far away. The sentence, "the movie was boring," and "the movie was amazing" differ only in the last word, but understanding requires connecting it to movie across the entire sentence. Long short-term memory networks, or LSTMs, were designed specifically to solve the vanishing gradient problem. The key innovation is the cell state, a highway that runs through the entire sequence, carrying information with minimal modification. 3 gates control information flow. The forget gate decides what to remove from cell state, the input gate decides what new information to add, and the output gate decides what to output based on cell state. These gates use sigmoid activations to create soft switches. The result is that LSTMs can maintain relevant information over hundreds of time steps, making them effective for long documents and complex dependencies. The gated recurrent unit, or GRU, is a simplified alternative to LSTM. While LSTM has 4 gates and a separate cell state, GRU combines these into just 2 gates, the reset gate and update gate. The update gate merges the functions of LSTM's forget and input gates. Despite having fewer parameters, GRUs achieve comparable performance to LSTMs on many tasks. They're faster to train and require less memory. In practice, the choice between LSTM and GRU often depends on your specific task and computational constraints. For very long sequences, LSTM might be preferred. For efficiency, GRU is often the better choice. Sequence-to-sequence, or sec-to-sec, models enable transforming one sequence into another. This architecture consists of 2 parts: an encoder that reads and compresses the input sequence into a context vector, and a decoder that generates the output sequence from this context. Sec-to-sec powers many applications: machine translation, text summarization, dialogue systems, and even code generation. However, the architecture has a bottleneck. All input information must be compressed into a fixed-size context vector. For long sequences, this compression can lose important details. This limitation motivated the development of attention mechanisms. The attention mechanism, was a breakthrough that addressed the sec-to-sec bottleneck. Instead of relying on a single context vector, attention allows the decoder to look at all encoder hidden states when generating each output word. It computes attention weights that determine how much focus to place on each input position. These weights are calculated using queries from the decoder and keys from the encoder, followed by a softmax to get a probability distribution. The result is a dynamic, weighted context that changes at each decoding step. Attention dramatically improved translation quality and provided interpretable alignments between source and target words. Bidirectional RNNs process sequences in both directions simultaneously. A forward RNN reads from left to right, while a backward RNN reads from right to left. Their hidden states are concatenated, giving each position access to both past and future context. This is crucial for tasks like named entity recognition, where the word bank could mean a financial institution or a river bank depending on surrounding context. We can also stack multiple RNN layers to create deeper networks that learn hierarchical representations. Combining bidirectional and stacked architectures gives us powerful models for sequence understanding. Let's summarize what we've learned in Chapter 2. We explored how deep learning transformed NLP, starting with basic RNNs that process sequences but struggle with long-range dependencies. LSTMs and GRUs solved the vanishing gradient problem with gating mechanisms. Sec-to-sec models enabled sequence-to-sequence transformations for tasks like translation. Attention mechanisms removed the bottleneck and provided dynamic, interpretable focus. Bidirectional and deep architectures further improved performance. In the next chapter, we'll see how these ideas culminated in the transformer architecture and BERT, which revolutionized NLP once again.